My name is Karungi Maria Daphine, and I want to present to you what our project is about. It's a credit card fraud detection system using quantum machine learning. So it basically solves the issue of credit card fraud. It can be in, let me say, you're trying to pay money using a credit card or in banks, supermarkets. So it solves this issue by using quantum machine learning, which integrates both machine learning and quantum computing to solve the issue. So Abstract has quantum machine learning, which offers improved fraud detection and focuses on computational efficiency and predictive accuracy. Then it has hybrid quantum classical approaches that enhance the quantum detection using anomalies. And it does this through different types. We have quantum neural networks, quantum PCA, which will be discussed further in the presentation. Then it also focuses on credit card fraud as a major financial threat to everyone. So the keywords we have here are quantum machine learning, quantum computing, the algorithms, the qubits, which are basically quantum bits that represent the ones and zeros, but this time they can be in many states simultaneously. So they solve the issue of processing speed faster than normal computers because they focus on appearing in two states at once. Then we have the quantum machine learning, which basically, as I said before, combines the machine learning and quantum computing, which basically means that it uses qubits to process data instead of ones and zeros, as I've said earlier on. Then we have a credit card fraud detection, which is self-explained. Credit card fraud detection detects fraud using credit cards. Then we have that's it. Thank you.
Podcast stopped. Fraud detection has relied on classical machine learning for many years, but the rising transaction volumes cause computational problems, as I'm going to explain more in the next slide. And the quantum machine learning leverages quantum properties like superposition. I'm going to show you what we call superpositions in the next slide, and entanglement to enhance and improve data processing on a transaction volume. And I'm going to be taking you in this next slide. Under the technical definitions that we have in our project, quantum machine learning combines classical machine learning with quantum computing to enhance data processing by leveraging quantum properties. Quantum machine learning can handle large transactional volumes more efficiently, as you're going to see. Then we have fraud detection, and this fraud detection it identifies unauthorized transactions by analyzing a number of patterns. A number of patterns can be like transaction date, amount transacted, such things. Then we have anomaly detection. Recognizes deviations in patterns, and it can enhance anomaly detection by analyzing amounts of data simultaneously. Then we have identifying subpatterns and correlations. That's how it can be performed. Then qubits, these are simply like they store data and process more data simultaneously. And qubits can be zeros or ones, as you can see here. We have just 0, 1, then we have 1 times 0, 1. Then that's what I have about qubits. Then quantum algorithm leverage quantum properties like superpositions, as I'm going to explain superpositions, what we mean by this, and entanglement, solve complex problems. This, Then after there, we have quantum computing. Quantum computing simply uses qubits to process information, and the quantum computers can handle vast amounts of data. Simply because what I was talking about superpositions, when we shift from a zero before we reach one, these are called superpositions, and superpositions can take a value 0.5 or 0.75 such digits in between zeros.
From where my colleague has stopped, then I talk about the current search trends. There are three. The first one is the variation quantum algorithm, for which it is one of the efficient process like one that processes data, processing complex data efficiently. For example, using the QK means clustering. Then we have the second one, the quantum annealing for deep learning. So for it optimizes deep learning models. For instance, it uses the neural networks. Then we have the hybrid quantum classical models, whereby it combines the above, like for it, combines strength of quantum and classical computing, like the two means clustering and then the neural networks. Then I went to the problem statement, then whereby we began with the past statement, which is meaning that the sophisticated fraudulent activities like cause a significant financial losses. That's when these activities occurs, like there's a lot of loss of like the financially people people loses a lot. Then we have the second point, the fraud detection faces quite a number of challenges. For instance, real-time constraints, high dimension data, high false positive rates, that all these ones that which causes unnecessary investigation, then the financial losses. Then we have therefore these challenges, the necessitated the requirements of the need for a quantum machine learning solution to handle the complex data, then the complex data detect anomalies in real time, and then they provide the real real-time results. So because of the above, like the financial losses that are being caused, so we decided to implement so that we can reduce only fraud that leads to financial losses. Thank you, sir. That's what I had. Then we welcome the next colleague of mine to continue.
Apio Diane, I'm going to be briefly taking you through technical challenges, proposed solution, and dataset description. We have a handful of technical challenges, but I'm going to highlight the key technical challenges, which is noise and error correction, as well as algorithm development. Quantum computers are prone to noise errors. And when we talk about noise, these are like random fluctuations that arise from the randomness and uncertainty of the fundamental laws of quantum mechanics. A little explanation: in quantum systems, there are particles like electrons, photons, atoms that exist in multiple states, which is known as superposition. Then, on the other hand, you have a phenomenon known as wave function collapse, in which a system, by interacting with the environment, is transformed from a superposition state into a definite or classical state with a well-defined value of a given measurable quantity. When we measure these particles, their states, so basically when we measure these particles, their states collapse to one of the many possible outcomes. The randomness and this fluctuations is due to the unpredictable nature of these measurement outcomes. And so overall, this just impacts the accuracy of the system. When you talk about algorithm development, you sort of highlight the key differences between quantum algorithms and classical algorithms, in which quantum algorithms are probabilistic in nature, and classical algorithms are deterministic. And of course, now there's a heightened need for effective innovation of efficient algorithms that can be implemented, and specifically in this case, and for credit card fraud detection. And this becomes quite of a huge challenge. And yes, but there are also other technical challenges. We look at our proposed solution. Our main solution is a hybrid approach of four machine learning concepts with an emphasis on quantum k-nearest neighbors for classifying transactions as legitimate or fraud based on their different features, quantum support vector machines for pattern recognition, and yeah, just basically recognizing patterns in transaction data that could be indicative of any fraudulent activity going on. And when we look at, uh, and of course, there's the neural networks and the principal component and the quantum principal component analysis. When we look at our data sets, we have one from Hugging Face and we have the second one from Data World. Both of these have both in both these data sets, principal component analysis has been applied to them, and sensitive information has been transformed into anonymous variables. And this has, of course, helped in noise reduction, dimensionality reduction, and has enhanced efficiency. When we talk about dimensionality reduction, it's the process of reducing the number of features or dimensions in a data set while preserving the most important information. Thank you.